We're going to talk about the first derivative test. If you have a curve that goes like that, like this, let's look at the tangent lines. Well, the tangent line at that point is negative. The tangent line at that point is negative. It's negative over here. I can draw that a lot better. It's negative over here. It's negative over here. It's negative here. The first derivative is negative. Now, for the record, the graph could have gone like this. The derivative is the slope of the tangent line there is negative. The slope of the tangent line at that point is negative. The slope of the tangent line at this point is negative. The first derivative will be less than 0. Note that if you have a negative slope, say a negative line, that slope is negative. This curve, all the tangent lines are negative, and all the tangent lines over here are negative. And this is just the same picture as up here. Now, we have the same thing going on if the curve goes like this or like this. In both cases, like in this case here, the functions are both decreasing. This function is decreasing. As I go to the right, it's going down. This function is decreasing. And f prime of x is negative. Over here, at that point, the slope is positive. It's positive. Over here, the slope is positive. Over here is positive. On the curve below, the slopes of the tangent lines are positive. They're all positive. F prime of x here is positive. The first derivative, when it's negative, it tells you the slope is decreasing. When the first derivative is positive, it tells you the slopes are positive. Why? Because the derivative tells you the slope. And every time in this picture here, every time you plug in an x value, maybe this is the x-axis and this here is the y-axis. You plug in this x value, whether you're here or here, the slope is positive. Plug in this x value, whether it's on the lower graph or the higher graph, the slope is positive. Keep in mind that those are two different graphs. I'm just showing you that the concavity doesn't matter. If the function is increasing, the derivative will be positive. If the function is decreasing, like it is down here, whether you're talking about this curve or this curve, the function is decreasing, which means the first derivative is negative. The derivative tells you what the slopes are. And if the slopes are positive, you have to be increasing. If the slopes are negative, you have to be decreasing. So you write down a function, and we're going to try to find out where the function is increasing and where it's decreasing. And the first derivative will tell us all of this. You compute the first derivative. When you bring this 3 down, it's going to get killed off by that 3 there. So you'll have 2x squared minus Derivative of x squared is 2x. We will factor out our 2x, and we get x minus 1. Now this equals 0 when 2 is 0, when x is 0, or when x minus 1 is 0. Well, 2 is never 0. I mean, if x is, I don't know, negative 2, what does 2 equal? It equals 2. It's ridiculous to say, oh, come on, 2 equals 0 because, you know, negative 2 plus 2 is 0. Who's asking you over here to add x and negative 2? If I ask you what x plus 2 is, then fine, you can say 0. So 2 is never 0. The fact that x is 0 when x is 0, and the fact that x minus 1 is 0 is when x is 1. So we want to know, so the only place where the slope can change value from positive to negative is where it equals 0. The slope can't go from negative 3 to positive 2. Can't go from negative to positive without passing 0. So let us figure out what is going on near 0. So we make the following chart. And basically you have a number line and you want to rule out or partition at 0 and 1. So you have 3 intervals: less than 0, between 0 and 1, and bigger than 1. So we'll look at from negative infinity to 0, from 0 to 1, and then from 1 to infinity. And we want to know if the first derivative is positive or negative. Well, the first derivative is made up of 3 factors. 2, well, that's always positive. X, the second factor, is only positive if x is bigger than 1, which is only in those intervals. It's less than 0 there. And x minus 1 is only positive if x is more than 1. That's only this last interval. Only those numbers are more than 1. Elsewhere it's negative. So the overall sign, I multiply those 3 signs, is positive, negative, and positive. And here's my answer. The function f of x is increasing on negative infinity to 0 because the derivative was positive. It is increasing from 1 to infinity as well because the derivative is positive. It is decreasing between 0 and 1 because the derivative is negative. Now, the graph, the best I can say is, we know it's continuous. So it's increasing up to 0, then it decreases up to 1, and then it increases again. I do not know how it does this. It can go like this. It can go like this. It can go like that. I don't know yet. That's what the second derivative will tell me. But all I know right now is that it is increasing. It is going up. So I answered the questions. It's increasing on negative infinity 0 as well as on 1 infinity, and it's decreasing on 0, negative 1. Suppose this time, okay, let us look at this function. Same question, find out where this function is increasing and decreasing. It's a cubic function. We take the derivative, which is 3x squared minus When you bring the 2 down, the 2 in the bottom kills it, so you have 3x. And if we were to factor out the 3x, we'd have x minus 1. Now, why does that look so similar to the last one? Okay. Let's change it a little bit. How about I just make this 6x? So we can still factor out the 3x, and then we're left with 2x minus 1. Okay, well, this equals 0 when the first factor is 0, which is never. When the second factor is 0, which is when x is 0, and when the third factor is 0. Well, 2x would have to be 1, because we all know that only 1 take away 1 is 0. So 2x is 1, so x is 1/2. So the only two values that came up are those two numbers. So we go from negative infinity to positive infinity, but we don't include 0, and we don't include a half in those intervals. We include every other number. And then we look at f prime of x in each of these 3 regions. And f prime of x is a product of 3 factors. The first factor is positive. Could have been -3. So we do have to take into account the sign of the product. X is positive only when x is bigger than 0, but that happens in these 2 intervals. But here x is not bigger than 0. It's less than 0, so it's negative. And 2x minus 1, well, that equals 0 when x is 1/2. And you know, if x is more than 1/2, if you double 1/2, you get 1. If you double more than 1/2, if you have more than 1/2 a dollar and I have more than 1/2 a dollar, together we have more than a dollar, and when you take away 1, we'll be positive. So it's only positive in the rightmost region. The other two are negative. So it's positive. Positive times negative is negative, and positive. It is increasing on this interval, it is decreasing in the middle, and it is increasing here. The best information I can tell you about this graph is first it's going up, then it's going down, then it's going up. The whole thing I just drew, it could have been a lot lower, or it could be a lot higher. In other words, if this is my XY axis, and I drew this, it may have been a lot lower. In other words, it may have been something like this. There's no reason why these ends shouldn't be going forever, because we are going to infinity and to negative infinity. But I can tell you for sure that first it's increasing, then it decreases, and then it increases. How about this problem? Suppose this time I give you this function. You have f of x equal to negative x to the 4th over 4 minus 5x cubed over 3 plus x squared over 2 plus 5x plus 13. And we want the derivative. Our hope is clear. When you bring the 4 down, it's going to cancel with the 4 in the bottom. so you just get x cubed. When you bring the 3 down, it's going to get killed by the 3 in the bottom, so you'll just have 5x squared plus x for the same reason plus 5. And it turns out that this is, when you factor it, you get negative 1 times x plus 1 times x minus 1 times x plus 5. Okay. Now, let's see what's going on. Well, this is equal to 0 when, well, the first factor is never 0. This is 0 when x is negative 1. This is when x is 1. And this is when x is negative 5. That's the smallest, that's the middle, that's the largest. So in terms of the table, you go from negative 5 to negative 1. I meant negative. You go from negative infinity to negative 5. Then you go from negative 5 to negative 1. Then you go from 1 to 1. And then you go from 1 to infinity. The only numbers that are not included is negative 5, negative 1, and 1. Every other number from negative infinity all the way to positive infinity are included. Every one of them. Okay, so now let us look at the sign of the first derivative. And before we do that, I just want to look at something in the last problem. Okay, I wanted to make sure that I answered the question, and I said where the function was increasing and decreasing, because that's still the same question. Where is the function increasing? Where is it decreasing? Okay, first factor is always negative. Finally, a negative 1. This one is positive only when x is bigger than negative 1. But that starts right here. To the right is bigger than negative 1. To the left is less than negative 1. X minus 1. It changes signs at 1. If your x is bigger than 1, you're positive. Well, you're only bigger than 1 to the right of this line. Positive, negative, negative, negative. And then x plus 5, that's bigger than 0 only if x is bigger than negative 5. The leftmost region is not bigger than negative 5, and that is why I should have put a negative. Glad I caught that. And the other regions are bigger than negative 5. So the overall sign will be positive, negative, positive, negative. For the record, they don't always have to alternate. So it's positive, negative, positive, and then negative. So it is increasing on negative infinity, negative 5, as well as negative 1, 1. It's decreasing on negative 5 to negative 1, as well as from 1 to infinity. This table tells you everything. It really does. Okay. How about you have the function f of x is equal to 3/5 x to the 5/3. We want to know where it's increasing. So we take the derivative. When you bring this down in front, 5/3 times 3/5 is 1 times x to make the new power 1 less. It's that. And 2/3 is positive. So this equals 0 when x is 0. So the table is a little bit shorter now. We only have to stop at 0. So we go from negative infinity to 0. We go from 0 to infinity. And we want to look at the sign of f prime of x in each of these intervals. Well, if you're negative, So x to the 2/3, that's the same as x squared to the 1/3. But x squared is positive, and the cube root of a positive number is always positive, always. So it turns out it's always positive. So the function goes up, and then it continues to go up. Okay, so where is it increasing? Everywhere. It's increasing. I hope I didn't say decreasing. It's increasing everywhere. One might argue it's not increasing at 0, but let's not talk about that. Why is it not increasing at 0? Because the slope is 0. Slope is positive, you're increasing. The slope is negative, you're decreasing. The slope is 0, you're constant. Okay. Let us look at the next one. Suppose you have that f of x is equal to 3/2 x to the 2/3. Well, f prime of x, you bring down the reciprocal, you'll get 1 times x to the negative 1/3. Remember, just do 2 minus 3, which is negative 1, and that's the numerator. Keep the same denominator. But this is 1 over x to the 1/3. It's never 0. A fraction is 0. A necessary condition for a fraction to be 0 is that the numerator is 0. But that numerator is always 1. But a critical point, which is what we really should be finding, is also when it's undefined. The prior problems we've done, the first derivative was never undefined. I guess I should have mentioned that, but go back and look. They were always well defined everywhere. So this is undefined when x equals 0. And there is no derivative when x is 0. Okay, so that's the only number that came up. So we're going to go from negative infinity to positive infinity, just stopping at the critical values. In this case, it's just 0. Just like in the last problem. However, this time, it's for a different reason. It's because the derivative is not defined. Okay. Now, if you take the cube root of a negative number, so we have a fraction going on, the numerator is always positive, it's 1. These numbers are negative in here. You take the cube root of a negative number, you get a negative answer. That overall fraction is negative. The numerator is 1. It's always positive. These numbers are always positive. You take the cube root of a positive number, you get a positive. So first the slope is decreasing, and then it increases. Let us look at the next problem. Suppose this time you're just given f prime of x. You're given that f prime of x is equal to x minus 4 over x minus 6. And I'm asking, where is f of x? Same question. Where is f of x decreasing? And where is f of x increasing? Well, this is 0. Fraction is 0 when the numerator is 0. That happened when x is 4. But make sure the denominator is not 0. Because 0 over 0 is not 0. Okay, but it's not. 4 minus only 4 gives you 0. So 4 minus 6, maybe we don't know what it is, but it isn't 0. And it is undefined. Didn't mean to write 0. It is undefined when the denominator is 0 but not the top. Well, 6 doesn't make the top 0. So these are the only two critical values. So those are the only two numbers we're going to stop at. You go from negative infinity to the smaller number, from the smaller number to the next number, and then from 6 to infinity. Every number is somewhere in one of those intervals, except 4 and 6. 4 is not in this interval because it doesn't include 4. 4 is not in that interval because we don't include 4. And 4 is not in this interval because the number 4 is not bigger than 6. Same argument with 6. 6 is not in any of the intervals. But the number pi is. Pi is in the first interval. Pi is less than 4. 21 over 5. That's more than 4. 4 goes into 20. 5 goes into 24 times. 5 goes into 21 more than 4 times. But clearly not 6 times. It's here. Every number is in one of those intervals with the exception of 4 and 6. And let us see what the sign of the first derivative is. Like the last problem, it's a slope. If you're less than 4 and you take away 4, if you don't have $4 in the bank, you have less than $4, and somehow you go to the bank and convince them to let you take out $4, you're negative. And if you're less than 4 and somehow you take away 6, the denominator is negative. Overall positive. These numbers are between 4 and 6. If you have more than 4 and you take away 4, you'll have something left. Well, but you're less than 6. If you have less than $6 and you take away 6, you're going to be negative. Negative. Now, numbers are bigger than 6. Well, if you have more than $6 and you take out 4, you have something left. If you have more than $6 and you take out 6, you'll have something left. It is the function f of x is increasing here and here, and it's decreasing here. So it's increasing on negative infinity 4, and it's increasing on 6 infinity, and it's decreasing in the middle. Now we're going to start talking about the second derivative. The second derivative, we're going to say the same things. Now, when it comes to the second derivative, first of all, a curve that looks like this is concave up. Now this is the function of f of x. Well, let's look at the slopes. It's negative, it's a little less negative, it's less negative, it's a little negative, it's 0, it's a little positive, it's very positive, very, very positive. You know, maybe here the slope is negative 100, and here it's negative 50, and here it's negative 1, and here the slope is negative a half, and here it's 0 and a half, and maybe negative 1 and 35 and 100. The change in the slope, it's increasing. It keeps getting bigger. From negative 100 to negative 50, it increased. It increased. It increases. Negative 1 to 0, it increased. It increased. Oops, that's positive 1. It increased. From 1 to 35, it increased. 35 to 100, it increased. The change in the slope, the derivative is the slope. The second derivative is the change in the slope, and it's positive. let's look at this curve. This curve, or any portion of it, is concave down. Well, here the slope is very positive, less positive, just a little positive. Here it's 0, negative, more negative, very negative, extremely negative. Okay, it went from positive slopes to 0 to negative. The change in the slopes are less than 0, or negative. It's decreasing, that is. Here, the slope is, I don't know, positive 100. Here is positive 50. Here, the slope is 3. Here, it's 1, 0, negative 1, negative 3, negative 50, and negative 100. The change in the slope, it's decreasing. It's getting less and less. That means negative. Now, I want to make this... Okay, so before I make something clear, if you just have any portion, you just have this portion here, that's concave up. If you have that portion, concave up. If you have this portion, concave up. If you have this bigger portion, concave up. Doesn't matter what part of that U shape you have. That portion is concave up. Now, on the other end, on the other side, you have the same thing. If you just have a small portion of the curve, like even if you just have that little portion there, if you just have this portion in yellow, that's concave up. This is concave up. This whole thing is concave up. This piece is concave up. This bigger piece is concave up. This whole thing, I meant concave down. I meant concave down. Any portion of this little portion, this big portion, it doesn't matter. Any portion of this is concave down. And the slopes are decreasing. The change in the slopes are decreasing. That's what I meant. The change in the slopes are decreasing. That is, the second derivative is negative. Now, I can't make this any clearer. Over here, notice I'm not saying the change in the slope. The slopes here are all positive. Oh, I get it. So when the first derivative is positive, that means the second derivative has to be positive. Well, no. Here, the slopes are negative. Here, the slopes are negative. That is, sometimes when the second derivative is positive, the first derivative could be positive or negative. I blew that one. It can be positive or negative. Knowing the second derivative does not tell you anything about the first derivative. To the left of this dotted line, these slopes are all negative. First derivative is negative. Yet, is concave up. That is, the second derivative is positive. On this half of that dotted line, the slopes are all positive, which means the first derivative is positive. But the second derivative is positive. You mean that if you know the sign of the first derivative, you can't, okay, let me not say this statement yet. let us look at the same thing on this side. When so here's this imaginary line. To the left of this line, all the slopes are positive. To the right of this line, all the slopes are negative. So now I can say the comment. If you come to know that the first derivative is positive, does it tell you anything about concavity? The answer is absolutely no, because here's a graph. Here is this graph where part of the region on this graph, the first derivative is positive, namely the right half, f prime of x is positive, and over here, f prime of x is negative. That is, just because you know the first derivative is positive, you can't conclude anything about the concavity. Likewise, if the first derivative is negative, like on the right side here, the first derivative is negative. Why would I write negative here? It's positive. And over here, the slopes are all negative to the left. Okay, again, the first derivatives can be negative or positive. Sorry, the first derivatives could both be, if the first derivative is negative, I apologize. If the first derivative is negative, it can come from concave up, or it can come from concave down. Knowing about the first derivative doesn't tell you anything about the concavity. And if you have the concavity, if you know the concavity is positive, look, the first derivative can be positive or negative. We have a concave up picture here, and part of it has the first derivative positive, and part of it has the first derivative negative. Over here, we have concave down. Sometimes the first derivative is negative, sometimes it's positive. Knowing the concavity does not tell you anything about the slopes, which is known as the first derivative. Knowing something about the slopes, that is, knowing something about the first derivative, tells you nothing about the concavity. Get that out of your head. There's no connection between them. None. Zero. Again, now that we're armed with this, if you know that the graph is positive, like we've been doing, maybe from 2 to 6, the first derivative is positive. Well, it is possible that the graph goes like this, and that is part of this, which is concave down. And everywhere on here, the slopes are all positive. But that is, f prime of x is positive. But the concavity here is different than this one. That green is part of this, which is concave up. You're going to say, which part? To me, looks like that part. And all these slopes are positive. Okay, so if the first derivative is positive, well, look at this. That's concave down. The second derivative can be negative, or it can go that way where the second derivative is concave up, which means the second derivative is positive. Okay, this is what's being held. And that is, the pink graph has positive slopes. The green graph only has positive slopes. that is positive tangent lines, but yet the purple function is concave down and the green function is concave up. You don't know anything from the first derivative to the second derivative. There is nothing that you can conclude. If you know the first derivative is positive, that's all you know. Okay. Now, let me just draw a couple of graphs. For example, that's concave down, and this is concave up, and they touch right there. Well, if we removed this piece of the graph and this piece of the graph, we are left with this blue graph. And there is this imaginary line right here, and to the left it's concave down, to the right of that imaginary line this portion is concave up. So you can have a function that has both concavity. And of course, the graph could have gone like this. And seems like right there, it looks like the graph is coming down, 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 and then it's going to go up. But it didn't. Likewise, coming from here, it looks like it's going to continue down. But once again, it didn't. That is, this graph has two concavities. Not at any one point. There's this imaginary line. To the left of the line, concave up. To the right of the line, the function is concave down. Okay, so give some functions, a couple of functions, and we're going to do the exact same thing that we did for the first derivative. The only difference is we won't stop after we take the first derivative and see where it's 0. We'll stop at the second derivative. Suppose you come to know that f of x is x cubed minus 3x over 3. So the first derivative, well, the constant 3 just stays there. The first derivative is 3x squared minus 3. You can factor out the 3, and it'll kill off with the 3 in the bottom. And then you can factor x squared plus 1 to this. And this equals 0 when that's 0, which is when x is negative 1, or that's 0 when x is 1. Oops, I didn't mean to do that. I apologize. We're doing the second derivative. So this is just x squared minus 1. So now we go to the second derivative, and we get 2x. And this equals 0 when x is 0. Okay, so we go from negative infinity to 0, and then from 0 to infinity. This was the only x value that made the second derivative 0 or undefined. And then we look at the plus minus sign of the second derivative. The second derivative is just a product of those two factors. 2 is always positive. X is only positive if x is positive. So it's negative here. So we get negative, positive. We have concave down. We have concave up. That is, this function is concave down on this interval, is concave up on 0 infinity. That's what this second derivative tells you, concavity. So there's really no difference here, except we went to the second derivative and we found out where it's 0 or undefined, and we made up our table. And we looked at their plus minus sign of f double prime of x. And instead of, when it's negative, instead of saying it's decreasing like we did with the first derivative, for the second derivative, we call it concave down. You know, up is usually good. Like you want your grades to go up. Down is not good. So good means positive and bad, down means negative. That is, if it goes up, if it's positive, this means concave up. If it goes down, if it's negative, that means down. That means concave down. Okay, maybe I should have just said up. Up is positive, good. Down is negative, bad. Okay, if I wanted to put good here, I should have put bad for going down. Okay, the second derivative is negative, is concave down. If the second derivative is positive on a region, that means it is concave up. Let us do one more like this. This time, I'll just give you the second derivative. No point in spending time calculating to their second derivative. But you do want to go to the second derivative. Okay, so once you have the second derivative, then you decide when it's 0 or undefined. It's 0 when the top is 0, which is at 4 or negative 4. 4 minus 4 is 0, times whatever is still going to be 0. And it didn't make the bottom 0. And when x is negative 4, this factor will be 0. So regardless that this is negative 8, when you multiply it by 0, you're going to get 0. And then when you divide it by negative 6, it's still 0. And it is undefined when the bottom is 0 at x equal 2. It's undefined at x equal 2. So these are our key numbers. That's where we want to stop the number line. So, maybe you want to put them in order. So you go from negative infinity to negative 4. Then you go from negative 4 to 2. Then you go from 2 to 4. And then you go from 4 to infinity. And you want to look at the sign of f double prime of x in each of these intervals. Each of those 4 intervals. And it is a division that we need to look for the sign of. Okay, first factor. If x is bigger than 4, it'll be positive. And only the last region is bigger than 4. The other ones are all less than 4. This factor, it is positive when x is bigger than negative 4. Starting from here, all of these intervals, the numbers are all bigger than negative 4. The last one is not. Okay, and now the denominator is positive only when you're bigger than 2. That happens only in the right 2 intervals. The other 2 are negative. So we have negative, positive, negative, and positive. So we have concave down, concave up because it's positive, negative is concave down, positive is concave up. The table tells you everything. The next thing we want to talk about is point of inflections. Let's see how I want to define that. And x value is a point of inflection. Okay. X equals c is called a point of inflection if the second derivative changes signs at x equals c. The second derivative changes signs at an x value. You have a point of inflection at that x value. For example, if a function is going like this, that's concave down, and then right there it starts to go concave upward, that point is a point of inflection, because to the left it's concave down, to the right is part of concave up. This is part of concave up, this is part of concave down. They meet right there in the middle. That's where you have a point of inflection. Now, some people may tell you you have a derivative that you have a point of inflection every time the second derivative is 0. Well, let's examine that. Let's examine that closely. Suppose you have y equal x to the 4th. Well, the first derivative would be 4x cubed, which for the record equals 0 when x is 0. You have a critical point there. And then the second derivative is 12x squared. And this equals 0 when x equals 0. Well, what's going on here? Do you have a max min, an extreme value at x equals 0? Or do you have a point of inflection at x equals 0? Well, let us look at both the first derivative and the second derivative at 0. Okay, so we look at the interval to the left of 0, which happens to be negative infinity 0. It could have been negative infinity to negative 1, and then negative 1 to 0. So I would talk about that interval. And the interval to the right of 0 is 0 to infinity. Only because there were no other values that made the first or second derivative 0. Okay, let us look at this. X cubed. So, well, 4x cubed. 4, that's the first derivative. 4 is always positive. X cubed is only positive when x is positive, and when x is negative, it's negative. And these numbers are all negative. So the overall sign will be negative. The overall sign will be positive. Ooh, look at that. We have a change in signs. It went from decreasing to increasing. And it being a polynomial is continuous. So we have a min here. Now let's look at the second derivative. Well, 12 is always positive. And as long as x is not 0, and it's not, that's the only number we're not including in the interval, x squared is always positive. Okay, there is no sign changed. It is always concave up. That tells me that when I go like this, in theory, I could have gone concave down and maybe concave up, or I could go concave down and then concave down again. But it turns out that I go concave up. Let me go a little bit lower. I go concave up, and I continue concave up. That is, let me draw it here, please. It's a nice U shape. I'm concave down. My slope is negative, then my slope is positive. And it turns out when my slope was negative, that I'm concave up. That's what motivated me to go this way. And then when my slope was positive, I was concave up. That's what motivated me to go this way, and for example, not that way. So I get this nice U shape. It's always concave up, so there's no point of inflection. Okay, so want to make the following statement, make it very clear. X equals C is called a point of inflection if the derivative changes at C. Second derivative. So if the second derivative changes signs at X equals C, you do have a point of inflection. On the other hand, if the second derivative equals 0 when X equals C, you may have a point of inflection at X equals C. You may have one. So, and you will not have a point of inflection when the second derivative is not 0. So, if you have the second derivative equal at X equals C, you need to go and see if you have a sign change. Did I erase all that beautiful work? Shucks. Okay, so let us do a couple of problems to decide whether or not we have a point of inflection. So we looked at this, but let's have this right next to x cubed. The first derivative is 4x cubed, which equals 0 when x is 0. The second derivative is 12x squared, which equals 0 when x is 0. Y prime is 3x squared, and y double prime is 6x. And this equals 0 when x is 0, and this equals 0 when x is 0. Now, let's look at what happens. With respect to the first derivative, at 0 or around 0, this derivative changes signs. If you have 4 times negative 0.001 cubed, this will be less than 0. But if you had 4 times positive 0.001 cubed, this will be greater than 0. That's for the first derivative. Now, the second derivative, as long as x is not 0, x squared is positive and 12 is positive. It's always positive around 0. Not at 0, but around 0. That is, there's no sign change. It went from a negative slope to a positive slope. You have a min at x equals 0. Okay, because the graph goes like this, and there's your min. You have no point of inflection at x equals 0 because the second derivative did not change signs. Now, let us look at x cubed. 3x squared around 0 doesn't change signs. It is always positive. Okay, so it's increasing and then increasing more. You have no max min at x equals 0. But this second derivative changes signs. If x is a little less than 0, 6 times a negative number is negative. 6 times a positive number is positive. Y double prime at 0 negative is going to be less than 0, which means concave down. The second derivative at a little bit more than 0 will be positive because 6 times a positive number is positive, and that implies concave up. So if here's your number line and here's 0, what do we know? First, it's concave down, so it goes this way, and then it's concave up, so it goes that way. In fact, it actually does that. It actually does that right at the origin. You all should know what y equal x cubed looks like. Y equals x cubed, if that's the y-axis, the x-axis, to the right of the 0 is concave up, and to the left it's concave down. So since the second derivative did change at 0, you have a point of inflection at x equals 0. So sometimes the second derivative equaling 0 gives you a point of inflection, sometimes it doesn't. I can't think of a function where, whether it's 0 or not, where the first and second derivative are 0 at the same point, and you have no point of inflection and no max or min point. But there are some very, very, very strange functions out there, and I'm always afraid to say you won't ever find one, or there is none. Okay, there's a function that's continuous everywhere. You can draw it without lifting your pen, yet the function is differentiable nowhere. It's differentiable nowhere. Okay, that's hard to believe, but it's there. You can find it. Okay. Let us do one more problem. One formal problem, node side-by-side graph. Suppose f of x or y is equal to this function. And we want to know if there's a point of inflection. So you find the first derivative, which is 4x cubed minus 12x squared. The second derivative is 12x squared. Now, anticipate that 12 is going to be a factor, because I already see the 12. So why don't we just go 2 times 12x? See the future. It's not hard. So I can factor out a 12x. So I have x left here, and I factored out 12x, so 2 is left. And this equals 0 when either 12 is 0, which is never, or when x is 0, which is when x is 0, or when x minus 2 is 0, which is when x is 2. Okay, so what we want to do is we want to look at the sign of the second derivative at certain intervals. And the numbers are in order 0, 2. So I go from negative infinity to the first value, and then 0 to 2, and then 2 to infinity. And the second derivative is a product of three factors. The first factor is always positive. X is only positive when X is positive, which is the last two regions, and it's negative in the first. And X minus 2 is only positive if X is more than 2, which is only the last region. So the other two are negative. Positive, negative, positive. We had, I don't want to draw that because it looks like I'm saying this what the slopes are. We have a change, positive to negative. Ooh, another change. So we have point of inflection at x equal 0. And we have a point of inflection at x equal 2. So both values had a point of inflection. The next video will talk about how to put the information from the first derivative along with the information from the second derivative along with whether or not you have a point of inflection, and we'll graph polynomials. See you in the next video.